Started. Sorry for the delay. First question is, are there any questions? Any questions or concerns, technical, logistical, about what's going on? Again, I fear there may be a Piazza apocalypse come where you're going to start to get requests for payment. I don't know if this has happened or not. Hopefully nothing embarrassing is happening. If it is, let me know. Okay, what else did I want to talk about? First thing is, I guess you now know enough to start on homework 1. Homework 1 is out there as an assignment. Are there people looking for partners? Okay. If you are looking for a homework partner, stand up. Okay. And I want you to look at the room and make eye contact with someone and shoot them a wave once you know who they are. And then sit down once you're a couple. And make sure that you have paired up. Okay, and you remember to find each other. Okay, turn around. I see several people standing. Okay, turn around. Okay, I'm seeing a lot of people standing, but not yet enough people sitting down. Okay, I'm going to give this for 30 minutes exercise, another minute. Okay, is there anybody, if you are for some reason unable to do this, come to me right after class, run up here, and I will pair you up here. Okay, so, again, I'm willing to help broker these marriages, but not act as a counselor. If that person does not prove to be a good partner, break up with them. Okay? Any questions? Okay, good. What other things did I want to talk about? I wanted to talk, the daily problem is important, but I wanted to finish up a little bit what I had last class before I go to the daily problem. So let me just try something here. We were talking about logarithms. And are there any questions about logarithms that came up, or on anything else that came up during class? I wanted to finish up talking about logarithms. There's one very, very important property of logarithms that I didn't get to. And this has to do with the idea that the base of a log isn't important. Okay, today, actually, that's a good question. Am I capable of writing on this? That's actually a good question. Okay. Let me just try this one more time before I give up as it being hopeless. Okay, we're going to have to write on the board today. That's fine. What was the property that's important about logarithms? It has to do with the fact that the base of a log turns out not to be important in a big O sense. Okay? As you know about logs, I described logs in terms of doubling, okay, or halving, repeated doubling or repeated halving. You could imagine repeated multiples of 10 or repeated divisions of 10. Okay? That would be the base 10 log. What's interesting is log of, for any constant, okay, log base b of n is going to be theta of log a of n. Okay? Okay? The base of the log does not matter. That's the important point. Now, why is that? Okay? Well, that's a consequence of this equation that's on the board that's kind of important to see. You may remember when you took in high school, you did see logarithms. You did get the idea that you could convert between the base of any logarithm by multiplying. That's what this equation is doing, right? Again, I wish I could write on the equation up there. But it says basically log base b of a is equal to log base c of a okay, divided by log base c of b. Okay? What does that mean? It means that if you want to convert between the log base b of a and the log base c of a, you have to divide by a constant. Okay? If b is a constant, okay, 2, 10, whatever, and c is a constant, 1.5, 100, 10 million, okay? You're going to convert between log b of a and log c of a. You're just dividing one by log base c of b. If c is a constant and b is a constant, the log of them is something you would get by punching on your calculator, okay? And so it's just a number, just a constant. So in a big O sense, it doesn't make any difference. These things are theta of each other. Okay? Any questions? So I'm going to sometimes talk about, it's no different if I talk about dividing something in half all the time versus dividing it by 4/3 versus dividing it by 99 100ths. All of these are going to be this big O of log n in height, okay? And that's an important property to have. Any questions? Now, where does this kind of thing come from? And again, these conversion properties are constants are surprisingly small, okay? So whether you have a perfect binary tree that always divides something in half, versus something that divides it 3/4, 1/4, 100 to 1, it doesn't really make much difference, okay? So long as you divide it by a constant fraction each time, the height is going to be log n. Any questions about that? Okay. I guess where does this come from? Well, I guess, okay, let me see if I can convince you of this. My claim is that C, okay, maybe I'm going to get my letters wrong, but let's try it. To the log B of n, C to the log C of n is going to be what? Does everybody agree that's going to be n? And what is B to the log B of n going to be? What is this going to be? Does everybody see that? So that means that C to the log C of n is equal to B to the log B of n. Right? Now what can I do? Can I convert B to C? I claim C, what is C raised to the log base C of B? What is C raised to the log base C of B? B. Does everybody see that's B? Does everybody see I could rewrite this thing as saying that basically n, okay, or C log C of n, which was n, is equal to, replace the B with this, C to the log C of B raised to the log C of n. Does everybody agree with that? And what does that mean? This thing, something raised to another power, you multiply the exponents. Remember that? This thing is really going to be C to the log C of B times log C of n. And that means that this exponent here is the same as the product of these two exponents. And from that, relabeling what I mean by A, B, and C appropriately, okay, you get the idea that you've converted a log of one base to the log of the other. Any questions about that? Hopefully that makes sense, but even if it doesn't, recognize that changing the base makes no difference. This is an important thing. Any questions? Okay, good. Let me see what else is there. Okay, hold on. I am somewhat terrified of this new machine. I'm grateful it is here, but what else do I know? Uh-oh. Okay. Logarithms are everywhere if you come to look at them. And this is one of my favorite examples, okay? I had a friend of mine who was studying for the bar exam or something like this, and he showed me this table that appeared in the federal sentencing guidelines. Okay? Suppose you give up your life in computer science and go for a life of crime. Okay? You get caught stealing a certain amount of money. How much time should the judge give you? The federal sentencing guidelines give you, basically, there's a book that the Department of Justice puts out telling you what the mapping of your crime is to what time people usually get for it. What do you notice here? This is a table of saying how many sentencing points, which basically maps to how many months you will serve, okay, maps to how much money you stole, okay? Can everybody see the table? What does the table say? Can anybody interpret it? If you look at the numbers here, the difference between each row, to me, looks like it's about doubling. 2,000 or less than 2,000, more than 2,000, 2,000, more than 5, 10, 20, 40, 70, 108, 20, 200. Does everybody see that whoever put this table together roughly doubled the amount of money required to achieve the next highest sentencing level? Does everybody see that? What's the interpretation? The sentencing level grows logarithmically in the amount of money that you steal. Does everybody see that? The punishment is going to grow logarithmically with the amount of money you steal. Well, what's the consequence of that? Well, basically, you should make the crime worth the time. Okay? If by doubling the amount of money you steal, you only get a few more months, what should you aspire to in your life of crime? Making one crime where you steal as much money as possible. If you're robbing liquor stores, this is a terrible thing to do. Each liquor store you get a punishment, and the punishment for getting your $3,000 from a liquor store is almost the same as if you embezzled $3 million from the university. So am I encouraging you to embezzle $3 million from the university? Not really, okay? But I'm encouraging you to see the consequences of where logarithmic growth is. The punishment grows logarithmic in the amount of money. It grows very slowly in the amount of money. That's why we like binary search. The time it takes grows logarithmically in the size of the the array you're searching. Any questions? Okay, any questions about logarithms? Okay, now let me see if I am adept enough to move to a different window. Okay, I'd now like to shift gears and talk about data structures. And it looks like we first have to do the problem of the day. Am I correct in saying this is the problem of the day? The problem of the day was saying, given two functions, f and g, find two functions that satisfy that relationship, if and only if it's possible. Okay? And let me show you how I would think about this. Okay? Well, first of all, you've got to remember what the definitions are. Big O is an upper bound. Okay? F of n equals g of n means that g of n is an upper bound on the function. Omega means that it's a lower bound on the function. Theta means it's a tight bound on the function. And little o, f of n equals little o of n, means it grows, not only is g of n an upper bound, but g of n is such an upper bound, okay, that f of n grows strictly slower than that. Okay? Any questions? Okay, so how would I deal with this problem? Okay, I need to give functions like that. What would be the way I'd think about it? I find these things complicated, so I've got to draw a picture. Why don't we start with the last two, 3 and 4, just because those are the ones that have the things you know more about, not the little o. What's this first one says? It's saying, is it possible that f of n is theta of g of n? Well, what does that mean? I'm going to draw a picture here. And here is my f of n. And what do I know if it's theta of g of n? It means that there is some constant c1 g of n that is bigger than it. And there is some constant c2 g of n that is less than it, right? Any questions? What is the second clause it wants to know for 3? Is it possible that f of n is not big O of g of n? This by itself shows this curve is an upper bound, right? This shows that f of n is less than c1 g of n. So yes, it has to be big O of g of n. Does everybody see that? And so I know that it can't be this case. This has to be a none. Any question about it? Does everybody agree this is impossible? Okay, and how did I do it? I reasoned about what was going on. Now, let's draw a separate picture. So for 3, it's none. What about for the second one? For the fourth one? Here I've got an f of n, and that's there. I think what you're telling me is that c times g of n is less than what you call f of n. That's what what you call it. F of n grows at least as fast as g of n. That's what the omega means, right? Does everybody agree that this is the picture? Now what's on the right? Is it possible that f of n, okay, is not big O of g of n? Well, let's just think about it. Is g of n an upper bound? For f of n to be big O of g of n has to be an upper bound. Is it possible for there not to be an upper bound? What if f of n was n squared and this was n? Does everybody see that that's true? Okay. F of n is not big O of g of n, and g of n is a lower bound of f of n. Okay? Do you see how I kind of did it? I drew the picture, and then once I did it, I could easily write functions that obey with that. Any things that differ in dominance relationship would do that. Any questions? Okay. Let's take a look at the little o ones now. What would I do for the first one? It says, suppose that f of n is little o of g of n. What does that mean? That means that g of n is here, and f of n is a tiny little thing that goes there. Does everybody agree? That's what little o of n means, grows strictly slower than. Is it possible that that's true, and f of n is not theta of g of n, Well, certainly f of n is not theta of g of n. It grows much slower than that, right? So what would I say is legal here? If g of n was equal to n squared, make it n cubed just for variation, and this was n squared, does everybody see that that satisfies the properties that we have here? Any questions about that? And what about the last one? Okay. The last one that remains said, suppose we have f of n is theta of g of n. What does that mean? That means there is some constant close to it, c1 g1, c1 of g of n, something c2 of g of n. I'm losing my mask. And what else is there? And we're saying an f of n is also so small. The theta is saying these guys are the same to satisfy little o of n. Okay? For f of n to be little o of g of n, it would have to be here. Okay? And it can't be. Right? Because f of n is theta of g of n. It's the same as g of n. For something to be little o of g of n, as it requested in the second one, f of n would have to be here. Okay, so if this was n squared, n squared, n squared, to satisfy the little o, I need this to be something like n, or maybe n log n. But it can't be because it's the same class. Okay? So this one is a none, and there's no way to do it. Any questions about that? With these big O things, again, I encourage you to just go, when you're confused, draw a picture, so you make sure you understand what the upper bounds and lower bounds are. And if necessary, go back to the definitions of, multiplicative constant, additive constant. Any questions about this? Okay. Okay, so let's now get into the algorithmic material. And again, I'm sorry that I've got a weird machine, and so I feel like I'm in a hostile environment. Okay. I'd like to now start a unit on data structures. Now, many of you are saying, I took CSE 214, I know all about data structures, and I hope you know all about data structures. Today, I'd like to give a review of much of what I think you learned in data structures. And maybe some other things to here, you took data structures before, okay? You worried a lot about the programming details, I hope. Okay? In algorithm design, we're going to be using data structures as kind of the building blocks that we build more complicated algorithms from. So we're going to want to talk here about stacks and queues and trees and heaps. And these are going to be automatic, sort of, building blocks from which we're going to build more complicated algorithms from. Okay? There was a quote I liked that said, mankind's progress is measured by the number of things we can do without thinking. The hope is that you learn and understand the details of these data structures, so you kind of know what they can do, and we can then go off and just use them. Okay? But it's important to understand what's going on inside. Any questions? Okay. So when you talk about data structures, there's, as I suspect you were taught in 214, there's kind of two different aspects of a data structure. One, there's the description of the abstract operations that a data structure supports. And two, there's the implementation of those operations. Note that for certain sets of operations, we're going to see many, many different ways of implementing it. dictionaries. We're going to talk about dictionary data structures next class. And there's many, many different ways of implementing dictionaries, some of which have advantages for certain circumstances, some of which don't. The same basic operations, okay, different implementations realize different performance trade-offs, okay? So recognize that, when you were taking, I think, 214, I suspect they talked about this idea of data abstraction, this idea that you can describe the operations of a data structure without describing the details of how it's doing it. So if we think about what a stack does, okay, a stack has two operations. You can push something on a stack, so it has the arguments of a, an item and the stack itself. Or you can pop something from a stack, which returns and removes the top item on the stack. Okay? This is the description of what a stack is. Now you can implement stacks in different ways. You can implement them using arrays. You can implement them using linked lists. There's probably other things you could do that are, different. But again, we're interested in the definition, and once you've got the definition, different implementations, and then we want to analyze the running time of those implementations so we can use them in other algorithms. Any questions? Okay, let's go down. So when I think about data structures, one way to break data structures into two classes is to talk about contiguous data structures or linked data structures. Okay? A contiguous data structure is something like a matrix or an array or a heap or a hash table. This is one where you allocate a big slab of memory and work in that big slab. The other kind of data structures were things built out of pointers, things built out of small chunks of memory that you link together with pointers. Okay? Linked lists are like this. Binary trees are like this. Graph adjacency lists are like this. Some data structures you can use a contiguous allocation. Sometimes you have to use pointers. How many people feel comfortable in their ability to use pointers? How many people don't feel comfortable in their ability to use pointers? A few, okay. So, this is something that it's important that we understand these data structures and why the pointers work, okay? Because again, we're going to be building things from this. So today I'm going to review pointers very quickly while talking about the properties of these different kinds of data structures. Any questions? Okay, what else can I say? First, let's talk about arrays. I imagine that everybody, sorry about that, liked arrays. Okay, arrays were so simple. Remember back to arrays? Okay, what was an array? An array was a slab of memory, okay, where each element could be addressed by an index. You had room for n items. You indexed them by a number from typically 0 to n minus 1, okay? And you could locate it, okay, in constant time. Why? Well, because every element in the array was of a fixed size. If you knew the location of the first element, if you knew the size of your elements in bytes, the computer could compute. If you said, I want the 17th, okay, element, where is it? It's where the first element is, times the fact that these are 4 bytes per integer, times 17. Okay, and that would tell you where it was. Okay, so what's good about arrays? Arrays had the property that if you have an index, you can find the thing in constant time. This is very good. You can't beat that. Arrays have the property that they consist purely of data, so there's no wasted space. When you have linked data structures, you normally have to store your data, plus you have to store pointers, right? And those pointers eat into your memory, okay? But arrays are pure data. There's another property that in big O world doesn't matter, but in real life now, maybe you should, again, we should be able to think in two worlds. You know that in real computers have these cache memories and all kinds of fancy things. It is often the case that the memory system grabs large hunks of data at the same time. And so if you're walking through an array, it's less expensive than if you are jumping around an array. Because you can often have the next element sitting waiting for you in cache, okay, even before you first touch it. So arrays turn out to be good things, sort of in modern memory systems. So if you can get away with an array, that's often a good thing. What is the bad thing about an array? Arrays sound great. What's the limit of an array? What's the problem of an array? Yeah? You have to know the size of the array at first, okay? If you need to have, why is it? You've got this complicated memory. If you allocate a big chunk of memory, to know how much memory you have to allocate, you need to know that amount in advance. And if you start filling in an array, and you need more, you can't just extend it because maybe this part of memory got allocated to something else. Does everybody see that problem? So the main problem with arrays is that you can't make them bigger. But have any of you ever used a programming language where they do make arrays bigger? In Java, do you have to tell people how big your array is? Okay. Many programming languages now support something called a dynamic array. What is the idea behind the dynamic array? You start filling it up, and underneath the hood of it, it allocated originally room for, let's say, 100 items. Fill, 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 fill. Oh, now I'm through with this. What do? One idea is, why don't I go and now allocate space for 200 items, and why don't I then copy over the first 100 items, and now have my array point to here instead of there. Does everybody see, by allocating a larger array, okay, I can get away with and recopying, I will, end up having an array where it's constant access every time. It's as big as I need it to be, right? What's the downside? The downside is how many times I copied. Does everybody kind of see that? But let's think a little bit more about analyzing this thing. What if I start with an array of size 1 and double it every time I need more space? If I'm ultimately going to use n elements, how many times did I recopy the array? Yeah? Log n. Why is it log n? This is important. Why is it log n? The number of times you have to double starting from 1 to get to n is log n, right? That's the log base 2 of n. Does everybody see that? You have to see where the log comes in. If I go through this doubling process, okay, I will have a total of log n doublings by the time my array gets to be size n. Any questions about that? Does everybody kind of see why it's log n? Now, how much work is done? Remember, I started out with one element, went to 2, went to 4, went to 8, and eventually I had to copy these, and then I had to copy these, and then I had to copy all of these. By the time it got to n, how much work did I do in copying this? Okay? Can anybody give me an upper bound and a lower bound? Okay? Imagine I'm inserting these items one by one, and whenever I run out of space, I go through this doubling process and recopy. How much copying do I have to do? Okay? A lower bound would be how much copy, what's the minimum amount of copying I can hope to get away with? Okay? Yeah? Okay, well maybe, okay, you said one element with 0 copying. How many total copying operations are there? Obviously, in the end, I've got an array that's of size n, and everything had to have been written in it, right? So this tells me that it should be at least n time, right? Because in the end, I've got n elements, I've got to write them, okay? Can anybody give me an analysis of how much time it takes to do all this copying in big O world? Does anybody have a sense of it? Yeah? You're saying n times log n. And that is an interesting answer. Now, why is that? This tree of copyings, it should be clear that there's log n operations, log n copy operations, right? And each of them involves at most n elements. Certainly something that is log n times, less than or equal to n is big O of n log n. Does everybody see that? That's the usual way we think about these analyzing things. What's the biggest cost times the number of things we're doing? And usually that lens gives us the right answer. But actually, no, look at this thing a little bit more closely. First of all, any questions? Second, look at this thing a little bit more closely. My claim is the first copying is only going to involve one element. Does everybody see that? The second copying is only going to involve 2 elements. Next one's 4. Okay? So what is the total amount of copying? And again, there's a couple of different ways of looking at it. One way to write that sum might be the total amount of copying is the sum as I goes from 1 to log n of 2 to the I. Let's just think if that's right. In the first thing, we're going to do 1 copy, right? In the second thing, we're going to go do 2 copies. Does everybody see that? In the third thing, we're going to do copy 4 elements, 8 elements. Does everybody see that this is one way to measure what the cost is? Okay, how many people see this? How many people don't see it? Nobody. Okay, so one person saw it, nobody didn't see it. Okay, is there any gap in between? Okay, it's a big room. Let's think about it. What do we know? The first copy operation was of 1 step, which is 2 to the, actually that's I minus 1 if I want to be precise, right? Or I could say 2 to the I as we go from, let's say, 0 to log n. Does everybody agree this is the number of copies? Any questions? What does this work out to? Does anybody know what 2 plus 4 plus 1 plus 2 plus 4 plus goes to? Yeah? Goes to 2 to the n minus 1. Well, let's think what's happening here. The first time we had 1 plus 2 is 1 less than 4. Does everybody agree with that? The next number, if we add 4 to it, does everybody see that this number is 1 less than 8? And if we now add 8 to it, does everybody see that that number is 1 less than 16? The interesting thing here is the sum of these numbers is really the same as the largest number in a big O sense, right? Okay, when you double this thing, my claim is all the previous stuff, okay, if you look at the last number we add is as big as the sum of all the other parts. Does everybody kind of get that? Any questions about that? If this is going to be the size of my array, let's call it M, this is going to be M minus 1. This tells me that the total amount of work that I do is less than twice what I would do if I allocated the whole array at once. That's what the interesting thing with this analysis is. Okay? And by doing that, okay, I now have the problem that, in fact, this procedure takes linear time, big O of n time, and not n log n time. N log n was an overestimate. Any questions? So the right answer is dynamic arrays are theta of n. Okay, so they're every bit as efficient as regular arrays. Any question in a big O sense? Any questions about that? Okay, good. Let me look here, and I'm afraid okay, hold on, somehow. Oh, actually, this is... Bingo. What other things can I tell you about data structures? Well, the other type of data structure that's important is something that is a pointer-based data structure, something which contiguous allocation, and with linked structures. What is a pointer? A pointer is an address of a location in memory. Okay? I think of it, you could think of it sort of, your cell phone number is sort of a pointer to you. If someone has their cell phone number, your cell phone number, they can reach you. You don't have to actually know where you are, but you're reachable through this pointer. They don't actually have you when they have the cell phone number. What they have is a pointer to where you are. Okay? And so linked structures are built by, okay, small pieces of memory that are linked together, okay, using pointers. And the pointer is the location in memory where we can find the next thing we care about. Now, I write my programs in C, for better or worse, and I know you guys may not be experts in C, but I think that the following pointers, what do we need to know? Star P, okay, is the item that is pointed to by P. If P is a pointer, star P is the item that's pointed to. And X, okay, and means address, okay, and X gives me the pointer of a particular value X. Okay, any questions? And there is a special null pointer, which points to nowhere, but is used to say when a pointer doesn't mean anything. Okay? It represents the end of a link. You shouldn't follow this pointer. Any questions? Okay? So let's look at examples of programs and how the pointers work on them. First, let's look at linked lists. This is a definition of a linked list, okay? The structure type of a linked list is that each element of a linked list consists of two things. It has a data field, which here is what I call item, and it has a pointer field. Here's what I call next. And a linked list here stores these items. Here's a 3-element linked list. The round circle is what points to the head of the list. The head points to the first element. The first element points to the second to the third points to nil, meaning it's the end of the list. Okay? Any question about it? So in a linked list, okay, each item contains a data field and a next pointer field. It's wasteful of memory in some sense, because we don't really like carrying pointers around. But it enables us to use little bits of memory to put a big data structure together. Any questions? Okay. What is a routine way to search in a linked list? Okay. Here is my routine. I hope you can read it from there. Let me try to read it to you. And again, I wish I could write on it now, but I do not have the technology today. What does this search procedure do? It is given two items. It's given two arguments. It is given a linked list, the L, a pointer to the head of the linked list, and it is given a key item that we want to find what is the record that has this key item in it. What is the way the procedure works? Well, if the pointer to the list is null, that means the list has nothing on it. If the list has nothing on it, it's going to, basically it certainly can't find it, and it returns null. You couldn't find it. Otherwise, you look to see, there's the pointer, the item field of what the pointer points to. That's what L points to item is in C. If that's the same as X, well, then then we return L as a pointer to the item that we care about. Otherwise, what are we doing? We're going to return the pointer returned by the search on the list without the first element. Notice this is a recursive procedure. The thing that is named search list, the bottom thing is named search list. Okay? Basically, this is saying, okay, either the list is empty, or the item is the first that you want is the first thing in the list, or let's go look at list.next, and that gives us a smaller list. And we're going to search for X in the smaller list. Any questions about that? Do people see? Yes? Is this thing going to return a list or an item? This is going to return a pointer to the item that contains X. That's actually what it's going to return to. Okay? Good question. It's not changing the list at all. It's returning the pointer. Okay? L, remember, is a pointer. Originally it pointed to the head of the list. We're going to advance it through the miracle of recursion to every single element. When it finds the right one, it's going to return it, and that's going to return it from all the levels of recursion. Any questions about that? If the list has n items, what is the running time of this algorithm? Okay, you should be able to read this thing. What is the running time of this algorithm? Yes? O of n. Why is it O of n?
Because worst case it goes all the way to the end of the list.
Okay, so the way I'd say is, I look at the first thing, This test, if the pointer is null, takes 1 computron. The test, if whether the item is, the same as x, takes 1 computron. It's then going to recur on to the next item, which now gives me a cost of an item that is 1 element less, right? I guess if you really want to get fancy about this analysis, if you don't believe it, one way to think about the cost, I claim the cost of this is going to be defined by a recurrence. If you're given an n element list, the cost of this is going to be what? O of 1 steps for doing the work. The recurrence is going to get us to an example that is of size n minus 1. And that's going to get something of size. That's going to be, if you go through and do this, okay, if C of 1 is 1, let's make this just to be precise, going to be 1. In this case, if you go through and work it, C of 2 is going to be equal to 1 plus 1. That's going to be 2, and C of n equals n. Okay? Any questions about that? This is linear because basically, as you say, it's visiting each element of the list and doing constant amount of work per element. Any questions? Good. What about inserting an item into a linked list? This is actually good practice here. Okay? Let's take a look and try to work this one out by hand rather than just copying, because I can't write on the thing. Suppose I have a list here. Let's make it 1, 2, 3. This is nil. Okay. Suppose I want to insert 2.5. Okay. Let's say I know exactly where I want to, okay, what if I want to, this is the initial pointer of the thing, which was L. Suppose I don't care about maintaining where I put it. Suppose I put it at the beginning. Here's my item. Let's call it, I think I said the other item was X. Okay. Suppose here, let's look at the code. Actually, it looks a little differently. X was a key. X was a data item. X was the number 5. I start by creating a new cell pointed to by P, okay? And I set the data field of that to be 5. That's what's happening in this malloc thing. See where I say P item equals X? What is the pointer operations I have to do? Given I know L points to the list, given that I know P is pointing to this thing, what are the operations that I need to do to bring this thing in? Okay? My way of thinking, I got this pointer that doesn't do anything. I think my first step is going to be P points to dot next should be equal to L. And now this thing points there. Does everybody agree? And now I say L equals P. Now L points to that. Does everybody see that? And now my item is in the linked list. Okay, how much time did it take to insert this guy into the linked list at the head? Okay, it did a constant amount of work, right? It didn't matter how long the list was. This was something that was constant time. Any questions about how I did that? Okay, good. What if I want to delete an item from a list? Okay. Let's say, what information should I want to have? Suppose I know that the item I care about, X, is here, okay? And I've got a linked list L that is pointing to this. How do I delete what X is pointed to? What do I need to do in this case? Okay, yeah, yeah.
Set the pointer of the one previous to the one next.
Conceptually, what I want to do is to take this guy and have that point to this. The moment I do that, item number 2 is gone. Does everybody see that? Okay. Again, I should eventually get rid of this thing because it's not going to do me any good once it's gone, right? But in order for me to do this, what I really need to do is to find the guy before me in the list and take that guy's next field, okay, and copy that and set that equal to my to what the element that I'm deleting, x dot next. What I want to find is the guy before it, let's call it P. I want to say P dot next should be equal to x dot next. And that's what this copy is. Any questions? Now, how do I get the guy before me in this list if I am just given X? Any ideas from elsewhere? How do I get that pointer? Yes. What was it? If I have a previous node variable, I have it. But right now, if you think about things in terms of abstract data types, I don't have that, right? The arguments to my item, delete operation, is going to be, I am given a pointer to my item, and I am given the full list. So somehow I've got to find this predecessor. And the way to do that, I claim, I need to find out what item is there ahead of the item. The interesting thing is that if all my pointers go this way, I've got somebody whose hands are on my shoulders, but I can't go back and reach them. I only can reach ahead. The way I've got to find this guy is I've got to go and look through the entire list to find the item that is ahead of me. How did I do that? Okay. My claim is I can find the item ahead. If I'm looking for a pointer named X, I have a pointer to an item and that pointer is X. What am I going to do? I'll start on L. L is the list. If L is null, or L dot next is nil, then there's no way that either of them can be a predecessor of X. I'm going to return null. But if what L points to dot next is X, then L is the predecessor. Okay? And I'm going to go take a look, return L. Otherwise, I'm going to do the same recursive trick and return the item ahead of X in the list that starts from L dot next. Any questions? What's the running time of this algorithm, the item ahead algorithm? Okay, on a linked list of n items. What's the running time? What? O(n). Okay, I'm spending a constant amount of work on each item, and there's a total of n items. Any questions? Once this is done, I can do my deletion. Okay, and what was my deletion? Well, basically just like what I said. I find pred is going to be the item ahead of me. If pred is null, then what does that mean? Then the only time pred would be null is if I have the first item that I'm trying to delete. If I'm trying to delete the first item, what do I have to change? I have to make L point to pred.next. And that's what I believe that says up there. Right? Otherwise, given the predecessor dot next is going to be equal to x dot next. Okay? And then I got to get rid of the node that I deleted. That's what free does. Any questions about that? People see how to do the mechanics of the deletion? Again, we're not going to be doing intricate pointer manipulations explicitly here because I'm going to kind of assume that you can do these kind of things. They're kind of elementary operations if you do them right. What are the advantages of linked lists? Why are linked lists good things? Well, one is the overflow in memory can only occur when the memory is actually full. Okay? As opposed to in an array where if you had a static allocation, once the array is full, you're out of business. Conceptually, insertion and deletion of elements can be simpler in contiguous structures. Notice that if I have an array of elements, big long array, if I delete this guy, I've got a hole. Somehow I got to get rid of that hole. If, let's say, I wanted to maintain the relative order, I've got to move all these items down, okay, and that's expensive and clumsy, okay? With linked lists, I really only touch the place where there's a problem. Any questions? Again, the key thing with dynamic memory allocation is it gives us the flexibility to use memory where we want it and need it, okay? And that's why we like linked structures. Any questions? Okay, good. There is also a question of whether we build, when we have a linked list, whether we build it as doubly linked list, where it points to both its predecessor and its successor, or singly linked, where we just point to the guy after us. Okay? Now, if you have two pointers going both ways, certain operations become easier. It should be clear that deletion would have become easier and more efficient. To get at the guy behind me in the list, if I had a pointer back there, then it was not a problem. I could get there in constant time. If the list only went one way, I had to walk the length of the list, potentially, to find that pointer. Okay? In a big O sense, the cost of maintaining lists as doubly linked is usually not something that matters. In a singly linked list, we had to use the space to store the key plus one pointer. In a doubly linked list, we had to store the space to hold the key plus two pointers. We double the amount of memory we need. That sounds bad. But doubling is just multiplying by a factor of 2. So big O-wise, big theta-wise, it's still the same, right? So if we need doubly linked lists, it's perfectly fine to have them. They don't cost us anything when we're dealing with big O world. In practice, if you go to your boss and said, hey, I just doubled the memory that our data structure is using, they may be unhappy unless there's a good reason for it. Okay? Any questions about that? Okay? And again, I think of the difference between these lists. In a conga line, you only are pointing to the person before you, whereas in a sort of typical dance line, you kind of point to the person before and after you. And so you can do more intricate things. Any questions? Okay, good. I think that's clear. What other data structures should I assume that you know about? Okay? I will assume you know about stacks and queues. What are stacks? Stacks are items where you are containers. They basically store items, but they don't let, you retrieve things from a stack or a queue based on the time of insertion, not based on the content. With linked lists, typically you're interested in storing items so you can look them up. With stacks and queues, you're storing items so you can process them. And the order in which you process them is based on when they were inserted. Okay? In a stack, we support last in, first out. Okay? We have basically a stack. Okay? When a new item comes in, we push it on the top. When we want to take an item out, we pop it off the stack. It's all the action is happening at the top. Okay? Any questions? A queue supports two operations. They allow you to insert an item at one end and to take it off to dequeue it from the other end. So when you say dequeue, you get the oldest item in the queue. In a stack, you get the youngest item in the stack. Does everybody get that? One of them is first in, first out. That's a queue. One of them is last in, first out. That's a stack. Okay? If you implement this using a linked list or an array, it will take constant time per operation. Any questions? Now, why do we typically, when we do this, I find it easier to represent a stack as an array because you're kind of doing all the operations on one end, okay? You won't fill the array naturally on a stack until you have actually filled the array. If you have a queue where things are getting inserted on this end and deleted on this end, okay, you could very easily have very few items in the queue, but gotten to the point where you have to kind of roll around the array. Okay, and so queues are all usually done with linked lists. Any questions? Why do we care about queues and stacks? This is the kind of question you should be asking in the algorithms class. What can I do with these things? Okay? Both of them are good for containers of items where the order doesn't matter. Sometimes the processing order does matter. When we talk about graph traversal, we're going to talk about breadth first search and depth first search. And it turns out that if we store our work to be done in a queue, we end up getting breadth first search. If we end up storing it in a stack, we get depth first search. And these turn out to have wildly different algorithmic consequences. Okay? There's also a question of what you're doing with the items. If you're worried about fairness, if you're maintaining a line at a bank, which is a better way to maintain the data structure? Should that data structure be a queue or a stack? Queue. Why is that? Because people get pissed off if the guy who came in later than them got served before them, right? Of course, if these are computer items don't get pissed off, so fairness may not matter. And like I say, if you think about what happens in my refrigerator, I think of a refrigerator as a stack. Why? When I have some leftovers, what do? I shove it in the fridge. When I have to retrieve food, I'm hungry. Which food do I eat? The stuff that's closest or the stuff that's furthest in the back? I usually grab the last item, right? And what does that mean? That's why the back of your refrigerator is someplace you don't want to look. Any questions about that? Okay. Any questions about stacks and queues, why we have them? Okay. Now, the most important type of data structure that we're going to talk about, in fact, it's going to be the focus of it all of next class, is going to be a type of data structure called, a data type called a dictionary. Now, dictionaries support 6 operations. And you have to understand what these operations are. Okay? Now, the first operation that dictionaries are good for are search. Here you're given as input a data structure, S, your pointer to the data structure, and you're given K, which is a key. A key is a data item, okay, to look something up on. Given the dictionary, what you'd like to do is say, is Skeena in the dictionary? What you want is a pointer to the record of the item that contains Skeena, right? Typically, why do you have a dictionary data structure? You have a key that represents something you can search on. There's probably auxiliary data that you care about. Like maybe for Skeena, if you're a bank, you want to know what his balance is, right? You can't search by who in the bank has $50 million. They organize it to say, how much money does Skeena have? Okay? It'll come out a lot less than that. Okay? Any questions? What's important? The search operation is defined on a key. All the other operations are going to be defined on the pointer. See that thing in red? In red, that is a K. Everything else is in black, and it's an X. The other operations start with pointers to things. Insert, you're given a record, you're given the dictionary and a record which contains the key and any other auxiliary data, and you want to put that record into the data structure. Does everybody see that? Delete. Given a pointer to the item in the data structure, okay? Delete that item from the data structure. What's great about this is, why does delete say, give me the item, give me a pointer to the item, rather than give me the key of the item you want to delete? Well, first you can always find that pointer by calling search. Does everybody see it? Given the operation, given a key, blow Skeena away. You decompose it into find where Skeena is in the data structure, followed by deleting Skeena. Any questions? Sometimes it's fast to find the item. Sometimes it's fast to delete it. Sometimes one is slow. Okay? We're assuming we have a pointer to what we want to delete in the dictionary. Any questions? What other operations are there? Max and min on a data structure tells us, returns a pointer to the element that is the largest in the set or the smallest in the set. If these were names, min would return the guy who's first in alphabetical order. Max would return the guy that's last in alphabetical order. Everybody see that? The last two are successor and predecessor. Notice that big word in red that says logical. This means that we want to know what element, the successor to an element, is what element appears right after it in sorted order. Not the one that is physically next to it. Remember we talked about separating logical data type, logical properties, the abstract properties, from how it's implemented. Successor is given a pointer to an item in the data structure, return a pointer to the guy that is next in sorted order. Predecessor means given a pointer to an item, return the item that's before it in sorted order. Does everybody see that? If you have an unsorted linked list, the guy that your L dot next to is not your successor, because there's no relationship. The guy after me, that I'm my successor, my neighbor in the linked list, if it's an unsorted list, does not necessarily have to be after me in sorted order. Any questions? So what's interesting, this dictionary data structure does about 7 different operations, and there's many ways to implement this dictionary. Yes, question?
Is it order based on keys or on values?
Is the order based on keys or values? The order should be on what I'm going to call keys, but I want to make sure I know why you're asking that question.
Just to clarify.
So typically, again, if we think about a data structure, if you're maintaining the bank, every item, there was a name and an amount of money they had, right? The name was the key, right? That's what it's sorted by. The amount of money is just baggage that you're carrying around that you want to associate with the name. The key property here is the key is the field that we want to be able to search on, want to be able to sort on. Okay, and any data values then are just baggage that are sometimes useful to carry around. Any question? Okay. What do I know? Suppose I implement a dictionary by an unsorted array. Okay, my underlying data representation is going to be an unsorted array. How much time will it take for each, if I implement it well? Here I've got an unsorted array, 17, 32, 6, 4, right? How do I search in an unsorted array if I want to implement the dictionary in an unsorted array? What was my search procedure do? I claim it is for I goes from 1 to n. If my key item is, 6, is the first item 6? No. I goes to I plus 1, is the second item 6? Third item, ding, ding, ding. Return 3, I, which was 3. If you were searching for a billion, it wasn't found, you return null. What is the running time of search in an unsorted array? O(n). What is the cost of inserting something into an unsorted array? Well, if I implement it, I better have a pointer or an index of what the last element is, or the first hole, right? If so, what do I want to do to insert it? I copy it into array of last, and then I set last equal to last plus 1. Okay? That's how I insert it into an unsorted array. How much time does that take? O of 1. What if I want to delete an item from a sorted array? An unsorted array. Okay? Remember, delete is given a pointer to the item, right? So I know that I have the index to this item. How do I delete it? Okay? One thing I